Alright, so here is the first part of homework 1-5. Hopefully we'll get through the first half or so. So two identical objects A and B fall from different heights to the ground, feel no appreciable air resistance. Object B takes twice as long as object A. Then they ask us to find the ratio between A and B. So this one truly is just boiling down to it's a free fall type thing, since we know that there's no air resistance. So if I'm looking for the ratio of their distances, I'm really thinking this relationship right here. The other nice thing about it is since both of these objects were dropped from different heights, so they were dropped from rest, I know the initial velocity is 0. So truly I'm just focusing in on this specific relationship. Now it doesn't tell me specific numbers. Obviously if you wanted to, you could plug in 9.8 and then you could just make up a time. You can make this 1 second, 2 seconds, whatever, and then double that time and then figure out how far it had to have fallen. And then that helps you set up a proportion. But I can actually do this generically too, right? So if I make my first position just based off of this, so 1/2 a t1 squared or whatever I want to call it, that's my first distance. If my second distance then takes twice as long, it would be 1/2 a 2 times t1 and then that whole quantity squared. So just like we've seen a lot going back to last year, and you've seen a few of going through the review questions from this year, the big thing we have to make sure we're paying attention to is the fact that the square would distribute to the 2. So this would actually be 1/2 a times 4 t1 squared. Now the other thing to watch out for, I know sometimes when you see the 1/2 and the 4, you want to multiply those together and say, well, it just ends up being 2 times as big. But the 1/2 didn't change, so I ignore the 1/2. I ignore the a because the a didn't change. And the t1 squared didn't change, right? So the only thing that changed was this extra factor of 4. So what that tells me then is x2 was 4 times as far as x1. So then the ratio of the heights, x2 is what I was calling hb, my second height, and x1 was what I was calling ha. So the ratio between those heights would be 1 to 4. So 1/4 is my correct answer. Question 2 here is actually kind of similar to questions, I believe, 6 and 7 from our last homework. They give us that a rock was dropped and it takes 3 seconds till it reaches the ground. So the significance of that first part, that first sentence there, they give me a means to find the original height of the cliff. They tell me that it was dropped, so I know my initial velocity is 0. I know the acceleration is 9.8 or negative 9.8. You can work with that as well. And then my time is 3 seconds. So that gives me a means to find the actual height then of the cliff, right? So if I just set up my delta x equals v sub 0t plus 1/2 at squared, I have enough measurements because my initial velocity is 0 to find my actual height. So I'm just going to set that up. So 1/2 9.8 times my time of 3 seconds squared. So then I get my delta x to be about 44.1 meters. So again, that's telling me the height of the cliff is 44.1 meters. Okay, so the reason that's helpful is the question's actually asking us what velocity does it have to be thrown with, so that takes 4.60 seconds. And they do ask us to include the direction. Well, hopefully it's obvious, right? But if it takes longer to throw it than it does to drop it, then I have to have thrown it upward. If I threw it downward, it would only speed this time up because it would be moving at a higher velocity, be moving at a higher average velocity. So it would take a shorter period of time. So I know that it has to be thrown upward. So that'll come into play when I get the direction. But then the reason I said this was similar to questions 6 and 7 is let's just identify everything we know. I'm looking for the initial velocity, but I do know that it's going to be positive because I'm defining upward as positive. It is very important here because I'm defining this as upward being positive that my acceleration needs to be a negative 9.8. I also know my initial height is 44.1 meters, and I'm going to use a positive 44.1 since it's above the ground. My final height would be 0. The alternative to this would be if you wanted to make this initial height of 0, you would make the final height negative 44.1, and it would be more or less the exact same equation. It's just already solved a different way. And then the time. They gave us the time right to work with. So they give us the time here, and then like I said, it's very similar to what we saw a couple times in the last homework assignment. So if we set up this relationship, just my delta x relationship, I just have my final and my initial as different positions. So my final was 0, this was 44.1, My initial velocity is not 0, that's what I'm solving for, but I know my time, and that's the big key. And then my acceleration was negative, so I'm going to write that as negative 4.9. And again, I know my time. So looking through this, the only measurement that I don't know is v sub 0. Okay, so at this point, it's just algebra, and hopefully it's pretty easy algebra, right? Just combine like terms, move it over to the other side, and then divide by 4.6. So when I calculate that, I get that to be about 12.95. The significance that it comes out positive does tell me that it is moving upward. Okay, so I do for sure know now that it has been thrown upward at a velocity of 12.95 meters per second. Obviously, if you called that about 13.0, that would be fine as well. So this question, the key here is obviously to iterate the difference between average acceleration and instantaneous acceleration. And again, the key difference, and I'll go ahead and write the answers down for those of you that want to check. The average acceleration should have been negative 2 meters per second squared, and the instantaneous should have been negative 7 meters per second squared. Okay. For those of us that want to see this worked out, the key here is the average acceleration. The average acceleration is defined as the change in velocity over time. So I do not want to find the acceleration function. I just want to work with my velocity function that they gave me. So the average acceleration during the first 5 seconds, if I want to find that, the way that I'm going to find that is I'm going to find my velocity at 5 seconds minus the velocity that I began with at 0 seconds. And then just divide that by my change in time, which would be obviously 5 seconds because it's the first 5 seconds. So I just have to solve for those two variables. So v of 5, I'm just taking 5 and plugging it in for t into my equation. So I have 2 plus 3 times 5 minus 1 times 5 squared. So when I get this, I have 2 plus 15 minus 25. And so from that, I end up getting a negative 8. So negative 8 meters per second would be that initial velocity at 5 seconds, not the initial, but the velocity at 5 seconds. And then my velocity at 0 seconds here, I do the exact same thing, except obviously this gets a little bit easier because it's just 2 plus 3 times 0, which obviously is 0, minus 1 times 0 squared, which again, obviously is 0. So my initial velocity was 2 meters per second. So then my change, my average acceleration, my change would be negative 8, the final, minus 2, and make sure you are paying attention to the signs there, then divided by 5. So negative 10 divided by 5, which is where I got my negative 2 meters per second squared. Okay, so that's where I got part A from. Again, the average acceleration, you do not use the acceleration function. However, for part B, to find the instantaneous acceleration, we do actually need to find our acceleration function. So if they gave me the velocity function, right, if they gave me this function, the key here is how do we go from velocity to acceleration? Well, hopefully we're comfortable with this by now. We've seen it several times. The velocity to the acceleration, I have to do the first derivative of the velocity. So the derivative cancels that out. I bring the power out front, and that t would go away. I'd bring the 2 out front, so it'd be minus 2t. So I end up with just this expression right here. And then if I want to find the acceleration at 5 seconds, then I simply plug in 5 for t. So 3 minus 2 times 5. So in other words, 3 minus 10, which is where I got my acceleration of negative 7 meters per second squared. So not a terribly difficult problem if you know what the question is asking for. Again, you need to be very comfortable with the instantaneous, you need the acceleration function, but the average, you actually just use the velocity function. And obviously this is a very, very key concept, and it's something we need to make sure we are comfortable with moving forward. Question 4. At first it looks like it's pretty similar to a question we worked in class where you're going to have to do a system of equations. However, this one's actually a shade easier if you pay close attention to the details. So if you want to check your answer, the final answer should be, the acceleration should be about 7.41 meters per second squared. Okay, so if you want to check that answer real quick, if you got it right and are confident, obviously move on. If not, I'll work it through. Okay, so speeding car traveling at 30 meters per second, so we know the car is traveling at a constant velocity, which is nice because the only equation I need for that is delta x over t. It passes a stationary police car, so we know the initial velocity of the police car is 0. The police car delays for 1 second before starting. What must the magnitude of its acceleration be for the car to reach the speeding car after 300 meters? So here's a couple of key facts that we have to make sure we're comfortable with. And one of them is the car has a 1 second head start. And so you do need to think about the initial position of the car when the police car starts to accelerate the initial position of the car is 30 meters because it's 30 meters per second times that 1 second. So it's 30 meters that it has a head start. Okay, other than that though, this one's actually a shade easier because I know that the final position of the car is 300 meters from where the police car was. So the car starts 30 meters ahead, and then the police car catches up to him at 300. I know the velocity of the car as well, so actually if I just start with this equation, I know the car was moving at 30 meters per second. It reaches a final position of 300 meters, but it started at 30 meters. And the reason that's so helpful is that actually gives me a direct means to find the time right now without needing to set up a system of equations. So obviously then just solving for the time, I get 300 minus 30, so 270, and then dividing by 30 when I flip these two in their positions here. So I get the time of 9 seconds. So the significance of that is it takes 9 seconds after the police car starts to accelerate for the police car to catch up with the actual speeding car. So then that's actually a vital piece of information that I can just jump in for the police car. So for the police car, let's identify what information we know. Well, its initial position was 0 because that's where I was defining it. This one had a 30-meter head start. He was at 0. His initial velocity was also 0. The acceleration is what we're looking for. We don't know the final velocity, okay, but we can usually work around that fact, right? I do know the final position was 300 meters because that's where he caught the car. And then again, the key here from my first part, I know that he catches the car after 9 seconds because that's how far the car had gone in 9 seconds. So anyway, at this point I have enough information to find my acceleration. If I use my position function, where I've got my final equals my initial plus the initial velocity times time plus 1/2 at squared, I've got all of the measurements here except the acceleration. So I know my final position was 300, my initial was 0, plus the velocity of the car, which was the police car, which was 0, plus 1/2 the acceleration, which I don't know, but I do know that it took 9 seconds, so 9 seconds squared. So then it's a pretty easy solve from this point, right? Just calculating 81, half of that, so 40.5, and then 300 divided by that, and that's where I got my 7.41 meters per second squared. Okay, so anyway, it gives me a route to find the acceleration, hopefully not too bad. Like I said, it looks like it's going to be a system of equations, but this one's actually a little bit easier for it. Okay, so question 5, if you want to check your answer for the first part, here it is. I am going to work the graphs out together though, so be patient with that. First part hopefully isn't too bad. We know the initial velocity of the car is a positive 30 meters per second since it's going up the hill. It does tell me that the slope is 10 degrees, which is significant because I can find the acceleration, right? I know the acceleration is going to come from gravity, but just the sine component of gravity. So if you need to build yourself that triangle to see this again, or just go back to the notes to review that, but that tells me that it'd be 9.8 times sine of 10, which comes out to be about 1.7 meters per second squared. I know the final velocity at the highest point is also 0 because at that moment it pauses before it starts to roll back down. So if I want to find the total displacement that it goes up the ramp, I have these three measurements to work with. I can work with my v squared equals v sub 0 squared plus 2a delta x, and simply solve for delta x. So my final velocity was 0. This was 30 squared. Now in this case I would actually make this acceleration negative 1.7 since it was working against my original velocity. So it'd be 2 times negative 1.7 delta x. And then solving this equation, that's where I got my first answer up here of 264.71 meters. Okay, so anyway, make sure you're comfortable with something like that. For the graphs, I think I will probably run short on time, so I will go ahead and pick up the graphs with part 2.